JWT is fast, but did you know highly secured systems such as the ones used in banks do not trust plain JWT? I'm Apollo Adeyeri, and let's explore different token strategies used by applications, particularly ones used in highly secured systems, and why most developers get it wrong. JWT is stateless, simple, and secured. It provides an avenue for developers to sign tokens with secrets, validate them, and undo expiration without having to store the tokens themselves. Now, this statelessness comes with its cost. When you generate tokens with JWT, you can't force users to log out, you can't kill stolen tokens, you can't revoke access once a token has been generated, and if someone by chance gets access to your secrets, you can't prevent them from forging your tokens and using them on the application. Now, this is just not secure enough for some applications like fintech applications and the rest. Now, let's take a moment to explore the way fintech applications and basically systems that require a lot of security tackle authentication with JWT. What we are looking at here is the typical authentication flow for most applications. It starts from the user logging into the application, providing their username and password or email and password. The server verifies the credential against the database, checks the password and sees if the hash is correct. And then when that is valid, a token is generated from the secret. And that token is sent to the user to be stored on the front-end application or the mobile application, whichever case it is. Now, for the concurrent request, where the user tries to access protected endpoints, the user sends their token as a part of the authorization header. Now, how this works on the backend is the backend has like a middleware that terminates every request that is protected, checks the token, and tries to decode that token using its own secret. Now, this same secret was previously used to generate a token that was sent to the user, and if the access token is valid, the decoding will be successful with the current secrets because it was previously used to generate the secret. Now, in the case that this decoding is not successful, that means the token that the user has provided is invalid and it has been generated somewhere else with a different secret. And then this request will be rejected. We would see here request to be rejected for unauthorized token or invalid token. And in also the case where the token decoding fails due to expiration issues, we would also reject the request because the token has expired and the user has to refresh the token by calling a refresh endpoint somewhere to refresh that token. Now, if all of this happens successfully, the token is decoded successfully and it's not expired, now the server proceeds to undo the business logic and returns a proper response to the user based on the endpoint. Now, this works fine for basic applications. It's very simple to implement, doesn't require so much compute capacity, doesn't require so much infrastructure to run, and it's completely stateless, so the application is simple to implement. Now, this is used a lot in applications, and in some cases, this does not suffice. In cases where the application requires so much security, deals with user user credentials or user data that should be protected, or finances like fintech applications. Now, this doesn't suffice for those kind of use cases. Now, let's explore token blacklisting. In this approach, revoked tokens are stored on the application and consequently checked whenever a user tries to use an access token to access the application. Let's look at how this flow works. First, a user makes a request with after logging in, a user makes a request with their JWT token. The API first checks the token blacklist by fetching from database or Redis. I think mostly for cases like this, for blacklisting, I think most applications use databases because you can't afford to lose the blacklist, which would be something that could happen in Redis. Now, after sending the request from the front end application to the back end, the application first checks that token against the blacklist and sees whether there has been any entry of that particular token on the blacklist. And if that is true, the token is rejected because this token has been blacklisted. It cannot access the application anymore. Now, in the case that a token is not in the blacklist, the application proceeds to verify the signature and tries to decode the token and also checking the expiry date. Now, in the case that the signature is valid and it's not expired, the application continues to run its normal flow and perform the business logic and response to the user. However, in the case that it's expired or the signature is not correct, the request is rejected. And if the token is expired, the refresh token is triggered, where the user refreshes their token and gets a new token to access the application. Now, when a user logs out, that's where the magic happens. When a user logs out or the token is compromised, let's say you keep track of the IP addresses where the user generates a token from, and you see the IP addresses is beginning to change. So user sends a request from their MacBook device. They're trying to use that same token on another device somewhere. That token is compromised, and you should prevent access to the application. Now, when a token is compromised or the user logs out, what the backend does is takes that token and just drops it into the blacklist. That's basically all. And then the consequent request checks the blacklist against these tokens. Now, this works fine. This is mostly used in applications where the login sessions are usually very long. There's like a long lifetime for the token, and you don't have a lot of logout calls. This is like used in some mobile applications or in some rare cases web applications also, where logout is not so frequent and the tokens often have long lifetimes. So this is able to prevent one thing. It's able to prevent revoke tokens, using revoke tokens. Like when a user logs out, they can no longer use that token again, even though it's copied and reused. Even though it's copied and you attempt to reuse it, it would fail and the request will be rejected. However, this does not prevent forged tokens. It cannot verify that a token has been modified with the stolen secret key. It still relies on JWT expiring the tokens manually. And there is a major problem with this. The major problem is the more users log out, the more memory that you use to store the blacklist. And this is just, it works for basic applications. However, as the application grows, as the number of users grows, and as the number of logouts grows, you begin to use a lot more memory, and it's just not scalable in the long run. This is not usable where you have millions of users or hundreds of thousands of users actually, where they begin to log out over and over and over again. This is just, it just doesn't work for those kind of situations. So, however, on the upside, it's very easy to implement. It handles logouts perfectly, and it doesn't change how JWT works. It's still mostly stateless, and it's just fine for basic applications and where dashboards that don't require so much security. However, it's still not strong enough for fintech applications. Token whitelisting or hybrid whitelisting is often used by highly secured systems to protect against stolen tokens or malicious attacks on their APIs. Now, the way that works is when a user sends a request to login, the access token and refresh token is generated, and those values are sent to the user. But before that, the API stores the refresh token alongside some session details like the IP address or the device agent and stores that on Redis. So preferably that is hashed just for security, because when it is not hashed, the token can be copied and reused somewhere else by whoever gets access to the tokens or to the Redis instance. Now, the basic access flow is still same. It still follows the same JWT structure. When a user provides the access token, the server validates the token, and the user gets access to the application without any other checks. Now, the difference is for this kind of setup, the tokens are often short-lived. The access tokens are very much short-lived, like preferably like 3 to 5 minutes. So your users have to refresh the token very often. And the magic happens when you try to refresh the token. When a user tries to refresh a token, they send their refresh token, and that refresh token that they sent is validated. You check against the signature, you check against the expiry, and as soon as that is done, you can now fetch the session ID, preferably from the token, and you can now compare this against what you have on Redis and see whether this refresh token is has an entry on Redis, whether it exists on Redis or whatever storage you use to store the refresh token. Now, when this happens, if the token is found on Redis, like if a match is found on Redis, which preferably you can use like the session ID to track as the key, just so it's easier to find. So when this is found on Redis, it means the token is fine, does not been invalidated, it's still valid, and the user gets access to the application and they're able to renew their token by generating a new access token. Now, in some cases, users also, some applications or developers also prefer to generate a new refresh token and rotate it. Then they have to update the Redis refresh token also. Now, the purpose of this is to make sure that whenever you refresh a token, you get a new refresh token also and a new access token, which means that the previous refresh token is now invalid and whoever gets access to that can no longer use it. However, this is not done all the time. Sometimes it's just the access token that is updated and the refresh token remains the same, and this works fine also. This is just based on preference and the needs of the system. Now, in the case that the refresh token is not found on Redis, it means either the refresh token has been invalidated, which means the session has been compromised or a logout has been performed, or maybe the token was never generated in the first place and it was just stolen, or it was forged from the secret key by someone who is like trying to maliciously get into the system. Now, the way this works also is the logout function means that whenever a user tries to log out, you go into Redis and delete their refresh token, which means that particular session cannot be refreshed. And also, this enables developers to implement features like logout all sessions or log out a particular sessions, because you cannot delete that item from Redis, and that is done for. So that's basically how that particular part works. Now, this also has its own downsides, because now it's not completely stateless, and whenever Redis goes down, it would mean that sessions would not work. As soon as the access token expires, you just have to log in again. So it's somewhat dependent on Redis. Application still works fine. However, users just begin to log in and log in and log in over again because Redis is not available in that case, or the refresh tokens are not usable. So it's somewhat stateless, but also it has this stateful part whenever you try to refresh the token. So this is like the best of both worlds. However, some cases require extreme precaution or extreme security. Now let's explore what that looks like in the next section. This here is an example of a very strict system where both access tokens and refresh tokens are stored on Redis, and anytime a user makes a new request, the token is checked against what's on Redis, and that can be used to validate whether the token has been revoked or not. Now the flow looks like this. When a user logs in, we check their credentials and generate a new session ID and use that to keep track of access tokens and refresh tokens and maybe other values like the user agents and things like that. Now, when these values are stored, they are stored on Redis, and on every consecutive request, the API first intercepts the request, checks whether the token is valid or expired, and in the case that it's not valid, which means the signature is not correct, or it's an invalid token, you can reject the token from there. Like the token, the request is rejected, and that ends there. Now, in the case that the token is expired, user refreshes the token, but we'll get to that later. In the case that the token is valid, what we do is extract the session ID from the token, the JWT token, and we also check against Redis. Check that against Redis. Use the session ID to check Redis for the particular session. Now, if that session is found, it means that we have found a session. We can now check the access token that the user has provided against the access token in that session. Now, when this check happens, of course, maybe it can be hashed or it can be raw directly, but it's preferable if it's hashed. We check the access token against the one in the session. If it matches, user has access to the application. Now, if the access token does not match what is on Redis, it means that the access token has passed the first validation, which is the signature check and the expiration check, but now it's not on Redis. So it means one of two things: whether this token has been revoked or it has been forged using the secret key. So one of those two things, and the token is rejected, because you have a token that is not expired, that the signature is valid, but I don't have that token on my service. That means that you must have stolen the token, or the token has been revoked on my end, and you can no longer use that token to access the application. So that stops there. And in the case where the token is expired, the user sends their refresh token to get a new access token to access the platform. Now, we check the refresh token, we fetch the session ID from the token, and then we check against Redis one more time. When we check against Redis, we see if the token is valid. Now, when it is, we refresh the token, maybe the access and refresh token together or just the access token, and we update it on Redis just to make sure we now have the latest one, and the latest one works to log in to access the application. Now, in the case that the refresh token is not called, it does not match, or the session is not found, you can also know that okay, the token has been forged, it has been modified, or it's just it has been logged out. And this also helps when tracking login sessions, because you can also show the user a list of all their sessions that are logged in, and when the user tries to log out all sessions, you just go to all the session that you have for that user, delete everything from Redis, and then that means that every token that the user has would now not work and not be refreshable for that particular user. Now this also means that you're able to track what session logged in at what time, and details like this that help you implement features like log out all sessions, log out this particular session on this particular device and things like that, because you can now track the sessions across devices and things like that. Now also you could invalidate tokens because the token has been compromised, like a user logs in from one IP address, tries to access the platform using another device, for example. So that could mean that the token is compromised, and that will be revoked. So this provides like a great deal of flexibility for the developer, because when a user logs out a request, that takes immediate effect. Unlike the previous setup where it's hybrid blacklisting and only the refresh token is stored. Now because the access token is also stored, when as soon as you click log out this session, every other request for that session fails without having to wait for the next refresh. Now that works perfectly in that sense, and it's very, very, very much robust and extremely secure in this sense. However, there are some heavy downsides to this. You are now depending heavily on Redis to keep track of your sessions, which will mean that you now have that particular overhead. Every time a request happens, you check Redis before the request continues to the service. And this adds like a few milliseconds on your request, and if this is important to you, then this is not your approach. But also, it also means that you would now drive up costs based on the way you use Redis for every single user that is logged in. Every single session that is logged in would now be tracked on Redis, which will mean extra cost on Redis also. And if for some reason Redis goes down, that means your entire application authentication system is down, and users will not be able to log in or use the login system. And also, it will mean that the more users you have logged in, the more data you have on Redis, and it's not very scalable in that sense. And these are just the trade-offs that we take in this aspect of programming, in authentication and in programming in general. Now, I hope with all of these examples, you are able to determine what exactly is best for your application. Now, this type of system, now the super strict system, is a very bad idea for your blog application or your to-do application, because it just does not fit the use case. Now, I hope this has been able to provide some insights to you as to what to consider when you're writing your auth system for your application. So that's all. It's all based on the needs and constraints like cost and infrastructure and things like that also come into play when you're deciding how to design your auth system, for example. So if you like the video, please go ahead and like the video, click the like button, and subscribe to my channel for more content like this. Thank you.